Hi, welcome to my channel, Dr. V.R.K. Reddy. In this video, I will be solving second order non-homogeneous differential equations with constant coefficients by variation of parameters. So, of course, all these problems are linear problems. This method is more stronger than the method of undetermined coefficients, and some situations is far better than the operator form as well. Let's see that what is this method and how to solve the differential equations using this variational parameter method. Equation y double prime plus p of x into y prime plus q of x into y is equal to r of x, and here we are trying to solve the homogeneous equation, equation y double prime plus p of x into y prime plus q of x into y is equal to 0, where these two are constants, and you know how to solve that, and the solution is of the form c1 e power, you can say that something into x. This something is real and imaginary also if the roots are complex, and similarly c2 into e power something into x if the roots are distinct. Assume that, or I can say that simply this is like y1 and this is like y2, then y is equal to c1 yc. Y complementary solution is c1 y1 plus c2 y2, where y1 and y2 are homogeneous solutions. Therefore, linear combination also a solution to the homogeneous differential equation. Now, to find ypi, we assume solution is of the form where v1 and v2 are unknowns, since the only condition is that y1 v1 plus y2 v2 has to be a solution, and but there are two functions involved in it, that is v1 we have to find, v2 we have to find. There is a lot of choice. Out of this many choices, the arbitrary way decide only look at for v1 and v2, which also satisfies a simple way, that is v1 prime y1 plus v2 prime y2 is equal to 0. We are assuming it, and then that leads to y is equal to v1 y1 plus v2 y2, and y, actually you can write it y or ypi prime you are finding, that is v1 y1 plus v2 y2 prime, and then v1 prime y1 plus v2 prime y2, but this is 0 because of this condition, leads to v1 y1 prime v2 y2 prime, and ypi double prime if we calculate, that is v1 y1 double prime plus v2 y2 double prime plus v1 prime y1 prime plus v2 prime y2 prime. And now you have, if you substitute in the given differential equation, you will be having ypi double prime plus p of x into y1 ypi prime plus q of x into ypi is equal to r of x, but the terms like v1 y1 double prime plus p of x into y1 prime plus q of x into y1 is 0 because of the homogeneous condition. Similarly v2 times y2 double prime plus p of x into y2 prime plus q of x into y2, this is also 0. So, therefore, you are left with v1 prime y1 prime plus v2 prime y2 prime, which is equal to non-homogeneous term, and v1 prime y1 plus v2 prime y2, which is 0 by one of the arbitrary choice. So here if you try to collect it, it is y1 prime y2 prime and then y1 y2. Of course you can write the other way, something like v1 prime v2 prime, which is equal to r of x 0. So here this is like y1 y2 y1 prime y2 prime is like your Wronskian, so which is a function of y1 comma y2, which is a function of y1 comma y2, that is the Wronskian y1 comma y2. This is like y1 comma y2, which is Wronskian, and therefore to get that solution, to solve it, you will be getting y1 prime is equal to y2 r by w, and v2 prime is equal to y1 r by w. This is with minus sign, and if you apply integration on both sides, v1 gives you minus y2 r of x divided by w into dx, and v2 is equal to integration of y1 r of x divided by w dx. So if you know y1 and y2, which are the solutions to the homogeneous differential equation, and w you are getting from y1 and y2, therefore you are able to get yp as v1 y1 plus v2 y2. Therefore y is equal to yc plus ypi is the solution to the given differential equation. So this is easy to handle, I mean very easy to follow. You can solve many varieties of problems. Some situations you can even solve the Cauchy-Euler equation using this method of undetermined coefficients, where Cauchy-Euler equation is a variable coefficient form. Of course it is a specific form. Now we will solve this problem. So what is the homogeneous solution? Roots are, let's say that yc is equal to c1 e power 2x plus c2 e power 3x. These are the roots to the given differential equation, homogeneous equation. So this is like my y1, this is like my y2, this is like my y1 and y2. Now yp is equal to, y particular integral solution is equal to v1 y1 plus v2 y2. So you know y1 and y2. y1 is e power 2x, y2 is e power 3x. You can take other way also, that is, or you can take, or you can take y1 is equal to e power 3x, y2 is equal to e power 2x. Solution is same, there is no difference in it. So don't bother about it, which one comes first, which one is coming later. Adjustment is based on that you are adjusting. v1 is equal to minus integral y2 into r of x divided by w dx. So if that is the case, the y1 is that, y2 is that, according to w definition, that is Wronskian y2 prime. So what is your y1? It is e power 2x, derivative of that is e power 2x. y2 is e power 3x, derivative of that is 3x. And if you simplify, that is 3 e power 5x minus 2 e power 5x, which is equal to e power 5x. Wronskian is that one. Now you try to substitute, minus y2 is, according to definition, e power 3x, e power 3x. r of x is given as x square e power 3x, x square e power 3x divided by e power 5x into dx, which is actually minus x square e power x dx. So this is your term. Now you have to apply bipartition method and all those things. That implies minus of x square e power x minus 2x plus 2 e power x is the solution. So therefore you will be getting minus x square minus 2x plus 2 e power x is the solution. So, you have to apply bipartition method, that is first step you will be getting x square e power x minus integral 2x e power x dx, and further it is x square e power x minus 2x e power x plus integration 2 e power x dx, and if you simplify this is leading to this one, this minus is carry forward over there. So, therefore, y1 is that, v1 is this. So, v2 is equal to integration y1 r of x divided by w Wronskian dx, that is y1 is e power 2x x square e power 3x divided by e power 5x dx, which is x cube by 3. Therefore, ypi is equal to v1 y1 plus v2 y2, that is v1 is equal to minus x square minus 2x plus 2 e power x multiplied with e power 2x plus v2 is x cube by 3, y2 is e power 3x. Now, if you simplify, this is also e power 3x, you can take common e power 3x, if you take common x cube by 3 minus x square plus 2x minus 2 is the ypi. Therefore, y is equal to c1 e power 2x, c2 e power 3x plus e power 3x into x cube by 3 minus x square minus 2x minus 2. There is an advantage with this method, you can even solve the differential equations of which are holding sin x, cos x, and then secant, tan, logarithm. There are many varieties of problems you can solve which is not possible, which are restricted actually using the method of undetermined coefficients. This is your homogeneous part, and the solution is y c yc is equal to, the roots are plus 1 minus 1 and minus 2, therefore c1 e power minus x plus c2 e power minus 2x. Therefore, you can take this is like y1 and this is like y2, and therefore solution follows that, and which implies v ypi, which is equal to v1 y1 plus v2 y2. Therefore, v1 is equal to minus integration of y2 r of x divided by w dx. So, you have to calculate the Wronskian. Wronskian is y1 y2, y1 derivative, y2 derivative. So, if you try to substitute e power minus x, e power minus 2x, derivative of that is e power minus x minus 2 times e power minus 2x. And if you try to simplify, this is minus e power minus 3x is the Wronskian. So, just if you substitute in that, you will be getting v1, v2 is v1 is equal to y2, y2 is e power minus 2x, r of x is sin e power x, and then divided by minus e power minus 3x dx, which is equal to integration e power x sin e power x dx. Therefore, the solution is going to be minus cos e power x. So, you can get it this by applying derivative. Therefore, v1 is this, to 2 is equal to integration of y2 r of x divided by w d of x, which is equal to y2, sorry, it is y1 is e power minus x sin e power x divided by minus 3x dx, which is after simplification e power 2x into sin e power x dx. And if you apply integration, this is like minus integration. If you try to apply like e power x is like t, you have like t square sin t dt. Let e power x is equal to t, therefore e power x dx equal to dt implies minus this is like t sin t, and here you have this is, you can write it as e power x sin e power x, and e power x dx. This is like dt, therefore you have dt. So this is very simple to handle, and this gives you after bipartitions cos t plus sin t, and which is equal to, if you replace t by e power x, like e power x cos e power x and minus sin e power x. So therefore with that you have yp is equal to, y particular integral solution is equal to minus e power minus x cos e power x plus e power minus 2x e power x cos e power x and minus sin e power x. So v1 y1 plus v2 y2. So if you, after simplification, this is minus 2x sin e power x is the ypi. Therefore, the general solution is y is equal to c1 e power minus x plus c2 e power minus 2x minus e power minus 2x sin e power x is the, this is the general solution to the given differential equation. This variation of parameter to solve the problems of variable coefficients also. So this is a specific form of this variable coefficients. We call this differential equation is Cauchy-Euler differential equation. So to solve these type of differential equations also, we can use this variation of parameters. X square y double prime ax square plus by bxy prime plus cy is equal to 0. See that derivative is multiplied with independent term of degree. Order and degree must be same. Order and degree must be same here, and there is no derivative, there is no x power non-zero term. It is x power 0. No derivative, x power 0 is multiplied. To solve these specific equations, we are assuming y is equal to x power m is the solution form, and y prime is equal to m into x power m minus 1, y double prime is equal to m into m minus 1 into x power m minus 2. Substitute in the given differential equation, you will be having a into m minus 1 plus b into m into m plus c into x power m is equal to 0. For non-trivial solution, x power m cannot be 0. I mean, here this y double prime, but y double prime is multiplied with x square into y double prime lead to x power m only ultimately. So therefore, I have taken x power m common, and that implies a m square minus a m plus b m plus c is equal to 0 is a quadratic equation. You have the roots like complex roots, real roots, and same roots. Real also there are two different, one is distinct real roots and then same repeated roots. All those things you will be getting these solutions, and then we are proceeding further to find the non-homogeneous solution. So we are solving this another example. Find the general solution to the differential equation 2y double prime plus 18y is equal to 6 tan 3t. So to solve this, first we are focusing on non-homogeneous differential equation, that is y double prime plus 9y is equal to 0. Then the solutions are y is equal to implies m is equal to plus or minus 3i, as m square plus 9 is equal to 0. Therefore, yc is equal to c1 cos 3t plus c2 sin 3t. Because it is independent variable is t, therefore I have taken everything in terms of t. And then Wronskian is y1, y2, y1 prime, y2 prime, that is equal to, so this is like y1 and this is like y2, therefore cos 3t sin 3t and minus 3 sin 3t and 3 cos 3t. So if you simplify, this is giving 3, as cos square 3t plus sin square 3t is 1. Therefore, your ypi is equal to v1 y1 plus v2 y2. So, v1 you have to find, but y1 is cos 3t, y2 is sin 3t, you know that. Therefore, is equal to 3 tan 3t. So, therefore, v2 v1 is equal to minus integration of y2. y2 is sin 3t, and then r of x is 3 tan 3t divided by Wronskian is w is 3. Therefore, it leads to a form like this minus 1 by 3 and integration sin square 3t divided by cos 3t dt. Okay, so this you can further simplify it as minus 1 by 3, 1 minus cos square 3t divided by cos 3t dt. So, you can further simplify it to integration 1 by cos 3t dt and plus 1 by 3 integration cos 3t dt. So, here this ends up with minus 1 by 3. This ends up with integration secant 3t dt plus 1 by 3, and integration of this is sin 3t divided by 3. So, therefore, we have additional term over there. We have y2 is equal to, of course, we have to simplify this part, and y2 is equal to integration of y1. y1 is cos 3t and then 3 tan 3t divided by 3 dt, which is equal to integration this cos 3t 3 cancel, sin 3t divided by cos 3t, as tan is sin by cos cancels, which is equal to sin 3t dt, which is equal to minus cos 3t by 3 here. So, if you substitute yp I is equal to v1 y1 plus v2 y2, that is equal to v1 is minus 1 by 3 times ln, you will be getting ln of secant 3t plus tan 3t for integration of secant secant 3t, and that is multiplied with y1, that is cos 3t, and similarly you have additional term that is giving like what is this term, plus cos 3t, it is y1, and this term is it. So, sin 3t by into sin 3t divided by 9 plus y2. y2 is sin 3t, but v2 is minus cos 3t divided by 3. This completes the solution. Is y of t is the general solution, c1 cos 3t plus c2 sin 3t minus cos 3t. If you try to take some terms out, ln of secant 3t plus tan 3t. So, the other term is cancelling. The other term is cancelling. That completes the problem. If you follow the concept, please like and share and subscribe the channel. Thank you.